Hello all, welcome to part 2 of the buffer overflow primer video series. In part 1, we had seen how it is possible to override the return address on the stack and control the EIP. In this video, we will look at how we can go ahead and create executable code which can be placed onto the stack. So without further ado, let's go ahead to the next slide. So what we saw in the previous video is that once we have the control of the return address which is stored on the stack, we can point it to absolutely any instruction which is there in the program memory. Now this could very well be our own executable payload which we have somehow managed to inject into the program memory. Now what is this payload? This payload is nothing but machine code which can be executed directly by the CPU without requiring any further assembly or compilation or whatever. Right, and this payload which we inject into the program memory, which is machine code, is what is called shellcode. Now the word shellcode was coined because initially this was almost always used to spawn a shell after the buffer overflow attack succeeded. So well, how do we go about writing this shellcode or the machine code which we can use? Now in this video we will concentrate simply on how shellcode can be written, the very simple example, right? So how do you do that? So the procedure is, first of all, write the code in C and create the executable. Now let's actually do this step by step. So let's write a very simple program called exit.c. And all this program is actually going to do is exit gracefully. Let's go ahead, compile this program. Now the reason I've used the dash static command line input is to make sure that all the libraries are statically embedded into the executable itself and there is no dynamic linking happening. Now let's execute the program, and as expected it simply exits, right? So now this is the very first part, as we saw in the slide, was to write the code in C and create the executable. Now basically in this exercise what we will do is create the shell code for the exit system call, right? So the second step is now to disassemble this executable and look at its assembly language equivalent. So what we can do is just load it up into GDB. Actually we should probably have let's go ahead and just load it up into GDB, and let's actually disassemble the main routine. And if you notice, all it does is going to call the exit routine, right? Let's disassemble the exit system call. So here is the exit system call. It is actually moving something from the stack to the EBX register. I think this is going to be the value 0 which was pushed onto the stack, which is actually the status value of the exit call. And then basically, if you notice, there are actually two system calls happening here. One is here, and this is the syscall number FC, which I think FC in hex would be 252 in decimal, and then another syscall is happening here, syscall number 1. So let's actually quickly open up a new terminal and look at exactly what these calls are. So depending on which machine you're in, I'm using a Slackware 12.2 version. This would be defined in one of these included files. right? So we saw the two syscalls. The second one is the exit syscall, right, with syscall number 1. This is what this is. And the other was, which was made initially, was the 0xfc syscall, which is 252. So let's actually search for 252. And if you notice, this is the exit group syscall, right? So basically what is happening is that there are two syscalls happening. The first is the exit group syscall, and then the exit syscall, which are wrapped around into the exit routine. So now let's go back to our slides again. So we've disassembled the executable. We know what is happening in the system call. The third is to remove the unnecessary pieces of code. So if we actually do a man, let's actually quit this, do a man on exit, we would actually see that exit goes ahead and simply terminates the calling process immediately. This is what we would want, right? And this is the second system call which is happening, right, which is this one. Now what is the first one doing, which is exit group? Let's actually just go ahead and look at its man page. And if you notice, this system call is equivalent to exit, except that it terminates not only the calling thread but all threads in the calling process. Fine, I think we can live without this and simply just call the exit syscall, which means this piece of code for us right now is unnecessary. We can simply get away by using this piece of code and loading the EBX register with the appropriate status value for the exit syscall. So let's quit this program and go ahead and write a very simple program now in assembly. I've already written the program, very simple assembly code. All it does is it has a start routine where we go ahead, load the value 20 into the EBX register, which is going to be the status value. Then we load the value 1 into EAX, which is the system call number for the exit syscall, and then we call the interrupt to go ahead and execute the system call, right? So this is what is required for the exit routine. Now going back to our slides, we rewrite the final code in assembly. This is exactly what this is. This is the only piece of code we want for the exit system call. And then is to use object dump to figure out the final shell code. Now if you notice, still right now this code is in assembler, right? So it is not really possible for the CPU to execute this code as is. We have to convert this into machine code, which is a combination of opcodes and operands. So how do we do that? We go ahead and first of all assemble this piece of code. Then we link it to get the executable code. And now we actually use the object dump utility. This should generally be installed in almost all Unix and Linux based systems. Comes with a package called binary utilities. In this we use the -d option, which is to disassemble the executable segments in the file which we provide to it. So we go ahead and give it the exit shellcode elf executable. So if you notice right now, here is the assembler assembly code. The 20 has been converted into hex, right? That is why it is 14. 20 in decimal is 14 in hex. And this is where the actual machine code is, right? This is your shell code, the BB 1400, so on and so forth. So if you actually notice, BB is actually the opcode which says, you know, move something into EBX, and the next 4 bytes is the actual value which is to be moved into EBX. Similarly, B8 is the opcode which actually says move something into EAX. That is what it instructs the CPU. And this is the final value, which is 1, which is to be moved into it, which is the operand. Okay, so now what we'll do is we'll just take this very simple piece of code and write and see how we can fit this into a C program, right? So let's use the other terminal and write a C program called shellcode.c. And what we do is we are going to define our entire shell code inside a character array. And because notice that all of these are hex values, we need to go ahead and use a switch to make sure that they are coming in correctly. Right, so we have BB14 followed by 3 zeros. And then what we have is B801 followed by 3 zeros. And then finally we have the CD80. So this is our shell code. Now let's go ahead and write a main routine. Nothing here yet, just want to make sure that everything is fine and this compiles okay. Okay, so I guess we can execute this. So however, if you notice, there is nothing much we can do right now because even though the shell code is there in the program memory, there is no way we have been able to figure out to actually execute it inside the main program. So what we will do is in the next video, we will look at how we can go ahead and execute this shell code from within the program itself. So I've tried to keep the videos a bit modularized so that none of the videos actually go above 10 to 15 minutes because probably people will lose attention and lose focus. So in the next video we look at how to execute the shell code. I'll be really thankful if you can leave behind some comments whether you liked the video, disliked it, so on and so forth. Thank you.